Welcome back, Chem 130 students. Chapter 7 is a long chapter, but we're halfway done. And now we're going to start on the shapes table that I told you to print out from either Canvas or the website. So we need this shapes table for this discussion. I want you to follow along. We're going to do valence shell electron pair repulsion theory, VSEPR. Basically, the premise is electrons are negative and they repel each other. Now, they're usually in pairs, like in a bond where there's two electrons in a bond, or a lone pair where you have two dots. But those lone pairs will repel other lone pairs or bonds because they're electrons and they're negative. It's really hard to take two negatives and push them together. Remember, if you try to push two negative magnets together, they push away, which is called repel. Electrons do the same thing. They push away and repel and try to get as far away from each other as possible. So the molecular shape of the atom is those bonds repelling each other. The bonds don't want to be close to each other, and the lone pairs don't want to be close to the bonds or other lone pairs. So they all push and spread out in 3 dimensions as far apart as they can be. Now, in our talk of valence shell electron pair repulsion theory, we're going to have the center atom be called an A, an outer atom is going to be a B, and a lone pair on the center atom is going to be an E. This is going to be our generic formula in the first column of the shapes table. So A, B, E. Remember, E is only a lone pair on the center atom. But before we get started, I want to mention, this isn't even on your table. If there's only 2 atoms, like the diatomic elements, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, the molecule is linear because you connect 2 points with a straight line. So 2 atoms connected with a bond, it's straight, it's linear. Like chlorine, as you can see right here, 2 Cl atoms, they got a single bond in the middle, it's linear. If they had a double bond or triple bond, it doesn't matter. It's still connecting the 2 atoms in a straight line. It's linear. That's not even on the table. So if you have 2 atoms, the shape is linear. Okay, now we're going to start with our ABE generic formula. So let's have a center atom with 2 atoms on opposite sides. No lone pairs on the center atom. So we're going to call that AB2. See, the carbon is the center atom A. This oxygen on the end is a B. The other oxygen is another B. So 2 B's, B2, AB2. So this is the first line in your table. AB2 is the generic pattern or formula. Then we have the molecular geometry pictured, which shows the 3 atoms in a straight line. It also shows the bond angle is 180 degrees. See, if you have 2 bonds, they want to get as far apart as possible, which is straight away from another, 180 degrees apart. So the bond angle is 180 degrees. And the name of the shape is linear. Name of shape is linear. That's the first line in your table. AB2. Looks like this. It's linear, 180 degree bond angle. Great. See, this is easy. This shape stuff is pretty easy. All right, let's try AB3. We have a center atom with 3 atoms around it. 1, 2, 3 atoms around the center atom. Okay, so that's AB3. Center atom with 3 atoms around it. No lone pairs on the center atom. Oxygen in the picture there has some lone pairs, but that's not the center atom. So this is AB3. It's the second line in your shapes table. AB3 looks like that. Looks like a triangle, doesn't it? If you connected the H to the O to the H across to the first H, it looks like a triangle. And the molecule is flat. So all the atoms are in the plane, a flat plane. So trigonal planar. Trigonal planar is the name of the shape. Now the bond angle is 1/3 of a circle. That's about 120 degrees. Okay, so 1/3 of the circle is the bond angle, 120 degrees. So again, there's a good example. There's a picture. It looks like a triangle. It's flat, so trigonal planar. Bond angle is 120 degrees for AB3. Next up is AB4. Now we have 4 atoms attached to the center atom. But this time, we're going to spread out in 3 dimensions. Now, if you look at the CH4 drawing, it looks flat. It looks like it's 90-degree angles, but it's not. If you look at the model here in the white and the black atoms, you can see CH4 is not flat anymore. We have a bond pointing out towards us and a bond going back behind us. So it's 3-dimensional. The bond angle isn't 90 degrees either. It's a little bigger than that. It's 109.5. So this is AB4. It's the 3rd line on your table. You can see the drawing there is in 3D, so it looks like that. Name of the shape is tetrahedral. Bond angle is 109.5. Okay, so if you have 4 atoms bonded to a central atom, no lone pairs on the central atom, it is tetrahedral. Bond angle is 109.5. It's 3-dimensional. It's not flat. It's okay if you draw it like the stick figure CH4, but you need to remember in your head, in reality, it's 3-dimensional. All right. Now, let's backtrack a little bit. Let's go back to AB2, but this time let's have a lone pair on the center atom, as we have with SO2. S has a lone pair up here. That lone pair is given the designation E. So this is AB2E, and it's the 4th line in your table. Now, what that lone pair up here does is it takes the bonds and pushes them down. So the bonds, instead of being out straight, the lone pair is negative electrons, bonds are negative electrons. It pushes those bonds down a little bit. So the O's are not across from each other. Okay, the O's point down a little bit because of the lone pair up here pushing them down, repelling them down. So the bond angle is actually a little less than 120 degrees between the O, S, and the O because of the lone pair up here pushing them down. So this is called AB2E. There's a lone pair on the center atom. That's the E. Looks like this in the table. Yes, it does. Name of the shape is bent. It's not straight across, it's bent. I know, that's a really scientific name. I always make fun of it. Bent. Who came up with that? Oh, it's not straight, it's bent. So, silly name, but the name of the shape is bent. Bond angle is a little less than 120 degrees. All right, move on. AB3E. So now we have AB3, but we have a lone pair on the center atom, as you see with NH3. There's a lone pair up here above the nitrogen. Again, what that does is it makes those NH bonds push down. So you can see the little shape here. The real shape is this blue nitrogen atom with the 3 hydrogens pointing down. It's kind of like a little pyramid, isn't it? It's a little pyramid. Now, the bottom of the pyramid is a triangle shape, but it's a pyramid. So it's trigonal pyramid, AB3E. When you have that lone pair up here, it pushes the bonds down and it turns the triangle into a pyramid. So trigonal pyramid. Again, that's the next to last row on your table. Looks like this picture. Yes, it does. Name of shape is trigonal pyramid. The bond angle is a little less than 109.5. AB3E. Last one, AB2E2. 2 lone pairs on the center atom. This one, our example, is water, H2O. So we looked at that Lewis-Stop structure earlier. Now, oxygen has 2 lone pairs up here. That really pushes the bonds down, so they get close, a little less than 109.5. Again, it's not straight. The bonds are pushed down because of the 2 lone pairs up here in water. So, AB2E2, center atom O, we have 2 H's, which is the B2. The 2 lone pairs is the E2. And again, if you look at the little red, white, model here, it's not a straight line because the lone pair pushed the bonds down, it's bent. So the name of this shape is bent again. The difference is the bond angle. It's a little less than 109.5. That's the difference between this bent and the other bent. That's our shapes. Thanks, JCC. Catch you later.